It's Nigel's last lecture is like Fermat's last theorem, but maybe not quite so not so famous. Okay, so I've shown you in the previous lectures. We've talked about patterns in space and time, particularly in time. So here is a summary of different types of explanations for periodic orbits, periodic cycles, showing you what they do and what is wrong with them. And last time we understood that demographic stochasticity is really the simplest explanation for them and underlies all of the possible bells and whistles that might want to try to put on these periodic oscillation models. And we also talked last time about how you can detect demographic noise in real data. This is a figure from another study. I'll talk about it later today. But basically, you look at the tails in the power spectrum, and they decay as omega to the -2, as opposed to what you would get if you had additive non-demographic noise. And in fact, I didn't have time to mention this last time, but this is actually observable in experiment. So these noise-induced cycles, they're called quasi-cycles. That's what many people call them. And you can see in experimental data, there's evidence for these power law omega to the -2 correlations in some of the data that we see, particularly in the Otto-Wolverine systems. Okay, so when does population discreteness really matter? It matters when the population size is small in a certain region where there's a high probability of extinction. So that can describe any system which is described by a density obeying a partial differential equation that will have solutions that, as the density gets very small, what will happen is this: in a discrete individual level model, as the number of individuals gets smaller and smaller, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Then it stops. By the way, I used to run a NASA Astrobiology Institute, and NASA likes countdowns, so that's why I knew how to count backwards from 10. And but if you have a partial differential equation, as you keep going down, what will happen is that the equation will keep on going, even though it should have stopped, even though there was only a fractional number of individuals left. So population size being small in a given region, where there's a high probability of extinction, that's where you absolutely need this level of description. And this can apply not just to the population, but it can apply if you're looking at a population coupled to mutants in the population. And so you need this individual level model. Another place where this matters is in invasion fronts or boundaries of spatial domains. Fronts get pulled by their tails, and so the front of, say, some population that is invading another region, the number of individuals may get small in the front, in the leading edge of the population invasion, and then that's where you also need to have the individuals. And the individual level description is important because if you solve those equations for a population front, you will get an equation for how they propagate, the speed. This is the so-called Kolmogorov, Petrovsky, Piskunov, Fisher waves. But if you solve them by PDE, you get the wrong answer by about an order of magnitude because of the discreteness in the tail of the distribution dramatically alters the speed at which a front goes. So you have to worry about the discreteness, even for something like a population front, where it's a continuum out here, but in the tail of the distribution, in the tail where the population is getting small, at the leading edge of the front, the discreteness has an observable effect on the macroscopic properties. And just for Johan, that's a prediction that was made by using Feynman diagrams. Okay, so there you go. You can tell your friends that. All right, and then lastly, if you have regime shifts or critical transitions, so we actually heard that patterns actually are some sort of maybe early warning signal, at least somewhat associated with the presence of a regime shift, a phase transition in an ecosystem, and those early warning signs will need spatial correlation functions. They will look at the behavior of the system when it's going from one phase to another. Then by definition, the order in the phase that it is going into is going to be small, and so discreteness will also matter there. So now we're going to talk about the stochastic Turing patterns. And yesterday we introduced a model called the Levin-Siegel model, which described plankton-herbivore interactions. And so that is where I want to start today. So let me rewind my notes here. Okay, so what we did last time was I introduced this model, and this model is a model that has a Lie effect. It has a density-dependent growth rate. This was this term. That's this term. Okay. So this term over here is not a logistic growth. E is positive. This is density-dependent growth rate. And then we also had predator competition. And remember I talked to you about the cartoon picture of what a Turing instability is, where you have an activator that activates not just the thing it acts on, but activates itself. And you have an inhibitor that inhibits not just the other thing, but also itself. And these are the terms in this plankton herbivore model that describes that. Okay, so now what? Okay. All right, so let's, now what happened? So let's leave it like that. Okay. All right, so now I want to do some Blackboard work, and then we're going to talk about some other things. So what I'm going to do today is I'm going to write down for you the stochastic individual level model for this plankton herbivore interaction, the Levin-Siegel model. I'll show you an outline of the calculation, and so this will be very thrilling for those of you who do theoretical physics. I'll discuss the predictions, and I'll discuss the regime of validity for these stochastic effects to be important. Then I will talk very briefly about how we verified these predictions. It took us about 5 or 6 years to do the work by looking at signaling molecules in a biofilm. And then lastly, I will talk a little bit about the work that we did on applying these methods to understanding hallucinations in the brain. Okay, so let me go straight on to the individual level model. So the individual level model, if you look at the terms that I wrote down, we can easily write what they are in individual terms. So I've got birth. I have this effect, this Lie effect, this density-dependent or number-dependent enhancement of the birth rate. I have predation, of course. And then I also have predator competition. So that looks like this. And then what you can do is you can write down the master equation that describes this, which I'm not going to do fully because it's a bit of a mess. There's a lot of terms. But I'll write just down one of them. So for example, the master equation looks something like this. So here's one of the terms. This is B times minus NB, P of NA, NB, plus NB minus 1, P of NA, NB minus 1, plus E over V, blah, 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 blah. Okay, so are there two different types of reproduction? Yeah. This one and this one? Yeah. Yeah? There are. Yes, it's called the Lie effect. when populations, when individuals are more close together, they have more chance to reproduce. Okay? If they're further apart, they have less chance to reproduce. It's happened to me when I had a girlfriend who lived in England. Okay? Okay, so it's called the allele effect. It's a very important thing in biology, in ecology. Okay, so now I want to explain to you something we haven't talked about, but some of you have asked me about it because I know you find it interesting, and you're right to find it interesting. So I want to show you the formalism that we use to try to turn this description into a field theory. So this is the thing that we don't want to do. What we don't want to do is write down a master equation. Here there is no space. Okay, here there is just numbers and time. But now we're going to do this this is a partial differential equation. Just to remind you, let's put the partial differential equation back up. It's a partial differential equation, and so what we would have to do is write down a master equation at every point in space, an infinite number of master equations, all coupled together. Okay, and even theoretical physicists aren't stupid enough to do that. Okay, so what instead we are going to do is we're going to use annihilation and creation operators from quantum field theory to write down a description of this system. So let me give you the outline of this. I'm not going to do this in full detail, and I'm not going to, there's lots and lots of technical points that if I were to spend the time doing it, we'd need another week or two of lectures. So I just want to give you the basic idea. And this is a formalism that was due to Doi. And then many other people helped develop it, including myself. Peter Grasberger, I think, is somebody who deserves much more credit than he is given. So I will mention some of the key papers later at the end. And what we're going to do is we're going to use the idea that when you have an annihilation and creation operator in quantum mechanics, you increase the number of particles in the system by 1. That's what we're doing here when we're looking at these step operators in these processes that are going on in the master equation. So what we're going to do is we're going to define a Fock space. And if you don't know what a Fock space is, that's fine. But this is definitely the point where if you haven't had advanced quantum mechanics, you definitely want to use this the next few minutes to check your email. Okay, so here's what a Fock space is. What you do is you say, what I'm interested in is the probability distribution for variable numbers of NA and NB. So what we're going to do is actually we're going to sum over these numbers, and we're going to have the probabilities be coefficients of a vector, what in quantum mechanics we would call a ket, and that defines a space that is like an extended Hilbert space, which has coefficients which are the probabilities that we want to do. So now we can define annihilation operators. For the predators. And I'm going to use a really horrible notation. When I wrote these notes, I was just thinking to myself, do I really want to do it like this? And I kind of wish I hadn't. But I'm going to stick with my notes or else I'll get confused. So annihilation is meant to work like this. Imagine that I have a state that is defined by the number of integers of m and n, the number of predator and the number of prey. So this is a state that has m predators and n prey, and then I'm going to act on this with an operator which I'll call A, and what that does is it reduces the number of predators by 1, leaves the prey unchanged, and if I were to act on it with an operator that I'm writing as A hat, and again, I apologize, this is a really stupid notation, and I regret it. That does m plus 1, n like that. So this operator increases the number of predators in the system, and the other one reduces the number, and then you can check that if I work out the commutation relations for these operators, I get 1 like that. This commutator, just to remind you, means A hat minus A hat A. Okay, so that's for the predators. I can do the same thing for the prey. So I'm going to call those operators C. So Cmn is equal to n, mn minus 1, and C hat of m and n is m into n plus 1. Okay, so that's how I've defined these operators. And then again, these operators commute. And if I were to write down the time evolution for the system, so this would be an arbitrary state, which is you can think of here as being a superposition of states with different predator and prey numbers weighted by their probability. So this is some arbitrary state in this space. I have to use a Fock space because normally in quantum mechanics you have a fixed number of particles. So we're doing quantum mechanics in spaces where particles can be created or destroyed, just like you have in relativistic quantum field theory. And so you have to use a space which is a linear superposition of all numbers of particles. So it turns out that I can write down the time evolution in the following way. It's like a Schrödinger equation, but it looks like this. D by dt of the state obeys an equation where I have an operator which I'll call L times psi of t, and this operator I call the Liouvillean. It's not really a Hamiltonian, and so some people call it the Liouvillean. Let me give you an example of how to construct this operator, how to construct the Liouville operator. And this, I'm going to use an example. If you want to read a bit more about it in a way that is reasonably user-friendly, I wrote a paper in JPhys-A in 1984. Well, I did the work in 1980 or something, but the work was published in 1984. And so this is just it walks through very simple examples of how to do this. So let's suppose I've got a species, A, and I'm looking at the reaction n copies of A goes to n prime copies of A with some rate k. So that would be a reaction that you might want to consider. So then you might say, well, I know what I want to do here because it's kind of easy, right? All I have to do is I've got to destroy n of these particles, n of these A particles, and create n prime of them. So what you might say is, well, this says that L is a n prime, something like that, with a rate k. So that would be the first thing that you would guess. That was the first thing I guessed as well. But there's a problem with that. If you do that, then the numbers just keep growing. You don't conserve probability. So you actually have to work out how do you write down a formula for the fact that all the probabilities have to add up to 1. And in the end, what it turns out that you have to add to this is a term on the right-hand side. So let me just write this down. So this here doesn't conserve probability. So I really want the sum of the probabilities to equal 1, and it's a disaster if that doesn't happen. So what we have to do is we have to subtract a term with a to the n, and it needs to be on the right of any creation operators. And that's what you need to do. Why? Because this times a creation operator is then a number operator, just like in regular quantum mechanics. So the term that you have to add here is a n like that. And then if I do this, then this thing is now correct. And if you want to do this, here is an exercise for those of you who like doing homework on the weekends. So you can check, and it's, I think, I can't remember if the algebra is in my paper or not, probably, or at least some clue. So you can check that if I write down this Liouville operator, so you plug this into here, when you do that, you use the algebra, what you do is you commute all the operators through and do the usual kind of quantum mechanics tricks. And what you can check is that the Liouville equation leads to the equation dp by dt of m and t, the number of particles of this thing, is of this form. So it's m prime sum of m prime p of m prime and t minus w of m prime m p of m. And this is a sum over m prime. So it looks something like that. So these w's here are the rate of the transitions. And as you commute all these operators through each other to get an equation for p through this equation here, you have these n and n primes here, multiple copies of them. You have to commute them through multiple times, and each time you do it, you get factors of n and m, which come from these terms over here. So what ends up happening is you get lots of things like factorials and things like this. So when you end up doing this calculation, what you end up deriving is that these rates for the transition from rate m prime to m, or whatever it is, goes like delta of k m prime plus n prime minus m minus n m prime over n and then n factorial. And I think this yeah, that's right. That's right. So this n and n prime, those are the n and n primes that come in over here and over here. So that's what those numbers are. So you tell me ahead of time what the rules are for this particular chemical reaction, and then the m and n prime. So these are the dummy variables that occur here and here. And then you get a thing like this, and you get all these combinatorial terms. And that's exactly what you would get if you were just asked a statistical physicist or mathematician who knew how to do factorials and combinatorics and so on. And so this is the standard formula that you will see in any textbook on master equations, and so you get that very conveniently from this formalism. Okay, so that's the basic idea. Okay. There's a lot more to it than that. There's a lot more that can be said, but that's the basic idea. Okay? All right. Then, so this is like second quantization. So now the next thing I want to do is second quantization for the Levin-Siegel model. So I'm just going to we're going to use these methods. We're just going to go through and work it out. So here is the answer. So it looks like this: c hat squared minus c hat c plus e over v c hat cubed minus c hat squared c squared plus p over v a hat squared a c minus a hat a c hat c plus d over v 1 minus a hat a squared. So that's all the reaction terms that are the polynomial terms in the Levin-Siegel model. And now there's something missing. What's missing is the spatial diffusion terms. So I'm going to put those in, and I also want to put in the fact that it's time dependent. So in the end, what I end up with is you get an action for this stochastic process, but now it involves space, so it's an action for a field theory, and it looks like this. And I'm not going to derive this because to do it properly would take a lot of work. But those of you who know a little bit about quantum field theory and so on will probably be noticing things here that look familiar to you. Okay, so this is the action, and let me then tell you how the action is used, and then I'll come to Owen's question. Pardon? My H is what? Wait, I can't hear you. Yes. 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 So, well, it's not actually. It isn't. That's why I didn't use the symbol L. So if I just had non-spatially dependent, I would say L. So now I'm using H to just represent the polynomial terms in the equation. And then if I were to write down L, so actually this is actually the L, this thing. In fact, this is the Lagrangian density. Okay? Does that answer your question? Yep. Okay. So that's the action. Now, what use is it? So what happens is that I can use this action to compute a generating function, which in equilibrium statistical mechanics we would call the partition function, but here I'll just call it the generating function. And so, do I have enough room? No, I'll do it over here. So what we do is you then generate any desired observable. Could be the mean value of one of the fields, it could be correlation functions, whatever you want. So I can generate any of those from the partition function or generating function. And so what I do is I have a functional integral over A hat, C hat, and then E to minus the action. Okay, so again, if you haven't done quantum field theory or had any exposure to this sort of advanced quantum material, quantum mechanics, this won't make much sense to you, and that's okay, okay? But for those of you who, some of you have asked me about all of this, this is what you do. So now I want to tell you what use this is. Okay, so just take this for granted that you do this math to formulate the discrete processes going on in space and time. Here's a way I want. Actually, here's a thing I didn't say, but is a true statement and is worth thinking about. In terms of the meaning of this, let me just spend a minute or two just to try to orient everybody in the room. If I have an ecosystem, so I have my predators and my preys sitting around like this, and now let's suppose that I say I'm going to now create a baby prey, let's say, at some point in space. So let's suppose it comes in here. So this is meant to be a new prey. And it's at this point in space and at that point in time. So what I'm doing is these annihilation creation operators here, they're generalized into space and time dependent operators. And so what I'm doing is I'm putting using a creation operator, which I call a hat, to create that particle there. And if I want to annihilate it, I'm applying an A operator. So these are field operators that act at points in space and time and create particles in the system. That's what happens in field theory. In field theory, you usually write down annihilation and creation operators in momentum space, and then you form combinations of plane wave states in order to get field operators in real space. So that's what we're doing here, and we're using that formalism. So that's what these things are useful. So everything, so what this does, this way of writing down the theory is a way to be able to say, I'm now going to sum over every possible history of the system, of every possible combination of particles being created and destroyed, predators and prey being created and destroyed at arbitrary points in space and time throughout the history of this ecosystem. So I am now able to construct every possible trajectory of the ecosystem in space and time, including particles annihilating and destroying and not being conserved and so on. And then I can work out from this what is the probability that these things, these trajectories actually occur. So let me just say that down. This formalism enables us to write out every possible trajectory in space and time of the ecosystem, and most importantly, and calculate the likelihood of each trajectory. So that's a question that we want to understand if we want to understand ecology. Okay, so now let me show you what we can do with this. So first comment I want to make is that this formalism is exact. This is not like, well, you know, I've done some physics approximation and it's quick and dirty as usual. This is exact. There's no approximation here. I've gone from writing down the verbal description of the problem to writing down an exact mathematical description. So this formalism, up to now, everything is exact. And that's what's really beautiful about it, because it means that we have an exact representation in terms of mathematics that if you've been trained in, one knows how to proceed. Okay, so let me give you one more thing. Let me compare this with quantum mechanics. So in quantum mechanics, the analog of this would be something like this. I would have some fields, or maybe the positions of a particle if it was quantum mechanics, and I would write the analog statement of this generating function would be a formula that looks something like this. This would be the classical action that I would get from classical mechanics for a field or for particles. There's an I over h bar, and then I do a functional integral over all the possible fields. And this was a formula that was first written down by Dirac nearly 100 years ago, and then was the basis for Feynman's picture of path integrals. S here is the integral dt ddx of the Lagrangian density. And usually the Lagrangian density is just the sum of the kinetic energy plus the potential energy, the terms that come into the Schrödinger equation. So what's cool about this is it looks exactly the same. And this is great because if you wanted to look at the classical limit of quantum field theory or quantum mechanics, you can see how to do that. And I want to explain that because we're going to use it here. So you can see that this is an integral. Even if you're not familiar with what this exactly means and how you would really do it, you can see that I've got in the exponential here an e to the I times the action divided by Planck's constant. So e to the I means it means that it's complex, so it's cosine plus sine, and so it's oscillating like this. So if I integrate an object that is oscillating, I'm going to get 0. Okay, so if I want to ask, well, how can I get a non-zero contribution to that? Well, that non-zero contribution can come from a trajectory which has a stationary phase. So the classical limit is you want to avoid the quantum oscillations. So what you do is you take the stationary phase of this integral, and what that means is you try to find configurations where this doesn't vary. And so what that means is you look for configurations where ds by d psi star is equal to 0. And if you take those equations, that those are the stationary phases of this, that gives you the Euler-Lagrange equations from classical mechanics. Okay. So now we're looking at statistical field theory. So when we look at statistical field theory, we don't really have the I in here, because this is a much better founded mathematical structure. But we then can ask, well, this is an integral. This integrand here will have a peak. It'll be peaked about some particular value of s. So if you look at the integrand, it might look something like this. And then what you want to say is, well, the largest contribution to this will come from here. So I'm plotting e to the minus s up here. And so what you want to identify is this point where the action s is not changing. And so this is the point where ds by d psi is equal to 0. And so this is the analog of this is the method of steepest descents. And so what it tells us that if we want to generate the deterministic theory from this fully stochastic theory, what we should do is look at the saddle point equations of this action. So I'm going to show you that in just a minute. So I'm going to actually derive for you from this formula that we've written down how you can get the Turing equations. Okay. So let me just say then, in statistical field theory, ds by d psi equals 0 gives you the deterministic equations. And then you can get the lowest order fluctuation corrections by expanding about the point, the field configurations which correspond to the deterministic solutions. So for those of you who know field theory, this would be the loop expansion. Okay, so now you might say, well, that's easy. I just take this formula here and I differentiate it with respect to A and C and so on, and then I will get the deterministic equations of motion. But that's wrong. That's not correct, because these operators here are raising and lowering operators. They're not the actual numbers of the particles. So in order to actually do this, we actually have to make a series of transformations on the problem. So the next comment is that we want to interpret the variables in terms of species numbers and things like that. But the annihilation and creation operators don't do that. So we have to make a bunch of transformations. And if you're familiar with some of this technology, well, what we're going to do is essentially turn this thing into a well, this is already a bosonic path integral. What we're going to do is do a Kohl-Hopf transformation and make this into a coherent state path integral. Okay, here's one other thing I didn't say, but so those of you who know field theory will know this. Once you've written this down, these objects, A and C hat and so on, those are no longer operators. They're just complex numbers. Okay? This is quantization not by using operators, but by using path integrals. It's much better. Okay, so we need a transformation, and the transformation that you have to do is not obvious unless you've seen this before. So you have to do this. A is Z, e to the minus Z. A hat is e to the Z hat. C is equal to rho, e to the minus rho hat. And C hat is equal to e to the rho hat. So those are the transformations that you need to do. And why do I want to do that? I think this is a row. Why do I want, I think there's a typo in my notes. Then why do you want to do that? Well, suppose I've got NA and NB predators and prey, then if I want to work out the expectation value of some function of those predators and prey, so I want to do that, then that turns out to be equal to the expectation value of the same function of the variables Z and rho. Okay, that's not going to be obvious. There's a lot of work that I've missed out here to show that that's the case. So these operators are the ones that I need. There's these other operators, A hat, Z hat, rho hat, C hat, and so on. For those of you who know, those things are what are called the Martin-Stidger-Rose response fields. Okay, but for now they're just variables. Okay, so let me write down. I'm getting near the end of all the technical stuff that I'm going to be talking about. So if you're falling asleep, that's fine. If you're checking your email, you should be winding that up in the next five or so minutes. Okay, so let me write down then in these variables what you get. So in these variables, S is the integral dt ddx of L, and now L is some god-awful mess. So here it is. It's Z hat d by dt Z plus rho hat d by dt rho minus dA Z hat del squared Z minus dB rho hat del squared rho minus dA Z grad Z hat squared minus dB rho grad rho hat squared, halfway there, plus B rho 1 minus e to the rho hat plus E over V rho squared 1 minus e to the rho hat plus C over V Z rho 1 minus e to the Z hat minus rho hat, and still got two more terms, darn it. Okay, plus D, yes, plus D over V Z squared 1 minus e to the minus Z hat plus predation P over V Z rho 1 minus e to the minus rho hat. Okay, and that's the end of the Lagrangian density. So you might say, well, that's a lot of work. My God, what does it mean? You know, but think about this. All alternatives to this are worse. I don't know any other way to do this calculation, and this way of doing it is simpler than most. Okay, so again, there's no approximations here. Everything is exact. Okay, it's fantastic that one can even write something down that is exact. Okay, so now I want to is going to get there's going to be algebra, but the conceptual component of it is going to be much simpler because I've already explained it to you in the last lecture. So the next thing we're going to do is I want to derive the mean field theory and if you remember last lecture, I had a same formalism as this, but it wasn't spatially extended. It was just at one point in space, just for a uniform system. And I showed you how the zeroth order expansion gives you the Lotka-Volterra equations. So I'm now going to derive the mean field theory and show you I get the the Levin-Siegel model as the mean field theory of these equations. And then I'm going to work out the equations for the fluctuations. And that's going to be very simple. So derive the mean field theory, and I'm going to be using the Van Kampen expansion. Okay, so let's do that. So let's go ahead with step 1. So what I'm going to do is, as before, now we've done, I've lost count of how many changes of variables. Now we're going to do what we did with the Van Kampen expansion. We're going to define new variables which are divided by the square root of v. So actually, what do I mean by this? I'm confused about my own notes here. I'm not sure. I don't know what. Wait. I'm going to erase that equation from the public record. Let's define z as equal to v times a plus the square root of v times eta. Rho is equal to v b plus the square root of v times psi. So these are going to be the mean field values. And then these variables here, psi and eta, for the predator and prey, are the fluctuations. And I think what I wanted to... Well, I'm just going to leave it like that. So now what we do is we take the Lagrangian density, and I'm going to expand that as the square root of v times L1 plus L2 plus terms of order 1 over the square root of v. So we're going to do the same thing we did last time. Expand the variables, expand the action, work to consistent order in square root of v, and we're going to see what we get. So what I want to do is we want to identify what L1 is and what L2 is. So our goal here is to read off these two things. So we're going to read those off by substituting this and this into the Lagrangian I've written down. So let me go ahead and do that. And now this is actually quite easy. So all you have to do is substitute these definitions into the, oh, I know what I wanted to say. I think what I wrote down is correct. All right, so all you do is plug in. And then we can read off the following. So L1 is rho hat d by dt of b plus z hat d by dt of A minus dA z hat del squared A minus dB rho hat del squared B minus B hat minus BB rho hat minus E B squared rho hat minus P AB Z hat minus rho plus D A squared Z hat. Okay. So that's what you get. So the mean field equation, so that's the part of the Lagrangian that is scaling the leading term, the part that scales in these units is square root of V. So then I want to get the mean field equations. So I get the mean field equations by differentiating. So what I set is dL by dz hat is equal to 0, and well, these are partial derivatives, not functional derivatives. So those are my steepest descent, my saddle point equations, these ones over here. So I set those things equal to 0, and then if you can even do this in your head as I write it down, and so you end up with dB by dt minus del squared B, minus dB del squared B plus B plus E B squared minus PAB, and this one gives you dA by dt minus dA del squared A plus PAB minus dA squared. So the mean field of these equations is the deterministic Keller-Segal model. So after all that, we breathe a sigh of relief. So that's good. So that's step one. Okay. So we already knew that. If we already knew that was true, that's not what we're here to do. We're here to calculate the fluctuation corrections. So now let me go and read off the fluctuations, and I'm going to write it down. And then the trick is that it's rather awful, but you can write it down as a Gaussian integral. And so that's the cool thing. So if I do L2, so that's the next order term in the Lagrangian density over here, then what I get is Z hat d by dt eta plus rho hat d by dt of the fluctuation psi minus Z hat dA del squared eta minus rho hat dB del squared psi minus P eta B Z hat minus rho plus 2d eta A Z hat plus B psi rho hat plus 2e psi B rho hat plus B psi A rho hat minus P psi A Z hat minus rho. I'm writing all these things down just so you can know that we actually did some work. Okay, it's not just writing down, oh, just phi squared and phi to the fourth, just put into some free energy. So there's some mess. I've no idea what it actually means, but this is how we can do the calculation. Okay, and now we're nearly done on all this. So what I'm going to do is I'm going to define a variable, a vector x, which I will define as the noise eta and the noise psi. Those are the noises specifically for the predator and the prey. So those are the noises. I'm going to define the field y hat. The field y is equal to z hat and rho hat. These fields that I haven't yet, that don't seem to have any physical interpretation. but they were just introduced as in terms of doing this calculation. And then this L2 now becomes beautifully simple. It looks like this. This vector y transpose d by dt vector x minus y transpose a matrix A, which I'll tell you what it is in a minute, minus x minus 1/2 y transpose b y. So that's what this Lagrangian actually turns out to be. And then these matrices look like this. Okay, this is in time, and also I need to tell you that I did a Fourier transform in space. So the Fourier transform in space just takes these del squareds and turns them into minus k squared. And so this A is a matrix that looks something like this: minus dA k squared plus pb minus 2dA, and then PA, and then minus PB, and then minus dB k squared plus B plus 2EB minus PA. So that's the matrix A. So everything here is calculated precisely, and the matrix B is something similar. I think what I'll do is I'll just simply not write it down. I think you'll take it for granted that I calculated it, and I want to show you what we do with it. So B is equal to another mess that involves A, B, k squared, and then E, D, B, dA, and dB. Okay, so it's another matrix, and it's in my notes. Okay, so why do we care about this? Well, remember that what we did last time was we took a formalism like this, and then we turned it into a Langevin equation. Yes?
When you take this Fourier transform in space, shouldn't some of these terms become convolutions, is the impression I get? Or am I... Because there's some cubic terms and things like that, right? So you Fourier transform that, it will not become just matrix multiplication, is my impression.
They don't, but can we talk about it privately afterwards? I don't want to get into a huge technical thing. Okay? I don't think so. Yeah. Okay, I can answer your question in a simple way. I just realized a simple way to see the answer. Okay, so to do this, to calculate these matrices, I have done what I said, but I also did another thing. Remember, I told you that we were doing an expansion. So remember that we expanded about the equilibrium value, not the equilibrium value, but the mean field values that come from here. Okay? Yeah, everything's the same as last time, but with infinitely more work. Okay? So that's where you, so good question. Are you happy with the answer now? Yeah. Okay. Great. Fantastic. Okay, so why do we do this? Well, we do the same thing like we did before. If I write out the equation of motion, you can see what's going to happen is I'm going to get d by dt. So when I do a Fourier transform, I'm going to get I omegas. So the Langevin equation that corresponds to this, going back to all the formalism I've taught you all week, you can just simply write it down as I omega x is equal to the matrix A x plus gamma. And gamma is a noise which has the following. What's going on with my brain today? Let's try again. So gamma has components, gamma 1 and gamma 2, and gamma I of omega, gamma j of minus omega is equal to the matrix Bij. So that's just that's just that. So again, what we do then is we take this, we can compute the power spectrum. So just like I did yesterday, compute the power spectrum. So I'm looking at power spectrum Pij is the expectation of xi, xj, something like this in omega. And I'm not going to write it down because it's disgusting, even more disgusting than any of this, but there's something very important about it. Its numerator is terms of order omega to the 6 and k to the 6, and the denominator is terms of order omega to the 8 and k to the 8. And you can work them all out exactly. Now, this is now important, because now what I'm going to do is if you've fallen asleep for the last 20 minutes or whatever, this is the time to wake up, because this is where we start to make real predictions. So this power spectrum, if I look at the power spectrum at large omega or large wave number, so what that says is that is going to look, so here is P, I could be plotting omega, or I could be plotting as K. So what I've just told you is I've got some mass, but it's got omega to the 6 on the top, omega to the 8 on the bottom. So it's going to decay here like omega to the -2 or k to the -2 if I'm looking in the space direction. Now, the question that we want to answer, why do we do all this? The question we want to answer is are there patterns? And the answer to that question is, well, if I compute the power spectrum, let's say in K, so I'm looking at the power spectrum along the K axis, we know it has to go down like this. If the power spectrum then, as a function of K, goes up like this, if this is true, then that will mean that there is a pattern, and then this will be the characteristic scale of the pattern. So I want to know, does the power spectrum actually have a form like this? Of course, I could just plot it out, but I can show you a quick and dirty way that one can evaluate it. So, so some people, just sort of plot this thing out, but there's a little trick that I thought of, which enables us to really calculate it quite simply. So the idea is this: if I have a pattern, if there is a pattern, and so I have a power spectrum that looks like this, then the scale of the pattern, the scale L, is when d by d k squared of the power spectrum of k is equal to 0, as long as it starts off at 0 down here, which it does. So I simply can compute d by dk squared and also d by d omega. And then what we find is that if it's positive, so if what I do is I want to look for a peak like this, but here at the origin it's got to be going up. So what I want to do is at the origin, at omega equals k equals 0, what I want to see is that dp by dk squared or dp by d omega is positive. Either of those things will guarantee that somewhere in the middle there is a point where I get this maximum. And so you have to do that calculation, and so you go ahead and do it. So there's a big mess, and then you calculate the criterion for patterns to form. And what that turns out to be is this. So last time I showed you what is the criterion for Turing patterns if they're deterministic, and then I showed you what is the criterion for them in the you know, I told you what happens if you have additive noise, and I worked out the criterion. So now we can work out the criterion for this this fully stochastic Turing theory, and you get something like this. I'm just going to write it down just to show you that after all the dust has settled, most of it has settled all over me actually, you end up with an expression that is quite simple. So that is the criterion, and if I use the values that I used before, which were b is 1/2, p is equal to 1, d is 1/2, e is 1/2. So what we found before was that d over dA over dB had to be greater than 28 for the deterministic patterns. And what it turns out to be in this case for the stochastic patterns is about 2.5. So it's an order of magnitude less. So it's incredibly easy to see the stochastic Turing patterns. So you do this calculation. So everything I've written down on this slide is what I just showed you. Okay? So it took me like half an hour or something to do. So this is the end result. I think I'm more or less nearly done with the calculation. So you can see here on the left, it doesn't work for colorblind people. Let's do this thing. Okay, so this is what I showed you before. This is the phase diagram for mean field theory for the deterministic Turing theory. And you can see that in this bottom part of the screen here, that's where the uniform state is stable. So you never, for any reasonable value of the coefficients, you never get a Turing pattern because you'd have to have a ratio of diffusivities. That's what this thing is in our paper. You know, over here it would have to be like a ratio of 60 or 100 or something like that. Okay. What happens over here? So this is what we just calculated. Okay, before your very eyes, missing out lots of algebra, but you got the idea. With demographic stochasticity, this gray area here shows you that stochastic noise will generate patterns in this area here. So it's much easier to get stochastic patterns. Okay, so the big take-home message is demographic noise qualitatively increases the parameter range that predicts patterns. Okay. If you want to work out what is the length scale, I'm not going to do it right now on the board. But it's in my notes, and the formula for it is the same formula that you get for the deterministic patterns. The formula is the same, but you're evaluating it in a parameter range where you wouldn't get deterministic patterns, but you're putting in the numbers that you would have for the stochastic Turing patterns. So you can work out that. Now, this theory has both K and omega, and I think I might have a picture of that over as the next. Why is that every time you put a laser pointer on, you can't do anything? Okay, here you go. So here's the power spectrum. So mean field theory, of course, has no power spectrum. The full theory has a power spectrum in K and in omega, and they are decoupled. So you can see here at K equals 0, which is the uniform case, there's still a peak in omega, and that's the peak of the quasi-cycles, the stochastic noise-induced oscillations. And you can work out the equation for that, and it's in my notes. And then over here, for omega equals 0, that's where the spatial patterns form, and they are decoupled. So you can calculate exactly these scales. And if you want to detect them, well, what you do is you look at the tails, because as I told you here, this thing goes as power 6, this thing goes as power 8, so all the asymptotics of the power spectrum go like k to the minus 2. If you have additive noise, which is the calculation I showed you last time, you get k to the minus 4, or omega to the minus 4. So they are different, and I showed you for quasi-cycles how you can see that just for the Wolverine ecosystem. Okay, so then I want to tell you one more thing. Nope, I don't think I want to do that. There was something I wanted to show you. Don't know what it was. Okay, so now I want to show you how they can be observed in nature. Okay, so I'm going to turn off the lights because I'm not going to use the blackboard anymore. Maybe one thing at the end. Okay, so so then we wanted to see. Oh, I know what I wanted to say. Okay, you can do this. You can do this calculation. So this was first done by us in 2009 and by Tommaso Biancalani and collaborators. References in my notes. In 2010, they took a different model. They took a model called the brusellator. It's a model of chemical reactions. I'll show you something about it in the slides in a little while. But the interesting thing about what they did was that when they solved it for their system, omega and k were coupled. So actually in their system, because of the way it was set up, you actually can have stochastically generated traveling waves. Okay? So here they're independent, but you can actually have traveling waves that are generated by the stochasticity, and that's what they found in their things. So that was Tommaso Biancalani's PhD thesis, and then he became my postdoc the following year. Okay. Okay, so we wanted to see if these could be done in real life. So then we did this work. This was I can't remember when it was published. Let me just get my pointer because I have one in here. It's okay, but it's in green, and I can see the bright big green spot, but not the little red spot. Okay. Okay, so this paper is the one I'm going to tell you about. A little bit later, Joel Stavens, who's a friend of mine at the Weizmann Institute, they also did a stochastic Turing pattern in a certain cyanobacteria. I'm not going to talk about that, but it's definitely worth taking a look at their paper too. So here's what we did. I'm going to be very brief about this because I want to talk about some other things. We took a biofilm which was in E. coli. We took signaling molecules from Pseudomonas, and we put dyes on these engineered signaling molecules, and then we let it go and took pictures. So what you end up getting is we had an RFP reporter to track one of the genes, a GFP reporter to track the others, and we could see in the different channels the different stochastic Turing patterns. So these are the patterns that you see. As I told you, they're not regular. They're not periodic, nice Turing patterns like you see in textbooks, but they have a well-defined length scale, and most importantly, they are not in the parameter range where you would get deterministic pattern formation. So we actually had to estimate all the parameters, and then we actually also built, believe it or not, a 20-parameter differential equation model to make sure that nothing that we were doing could be in the deterministic range. Then we computed the power spectrum, and again, these were consistent with a -2 power law scaling. Okay, and then here's a comparison between an experiment and theory. So what we did here was we had a 20-parameter, very detailed model. Normally I don't do these detailed models, but I wanted to really just check whether, if this was all stable, if this was robust. So then we fitted all the parameters, which we did by doing Latin hypercube sampling, and then these are the results of experiment and simulation, and it works very well. Okay, so one thing I want to just very quickly mention, I'm not going to go through it in detail, was you might say these stochastic patterns can't possibly be observed. Okay, and here's the reason. The amplitude of a pattern is going to be determined by the amplitude of the noise that is forcing it. And if the noise is just some fluctuations or whatever, if they're locally small, then it's just going to mean that you'll never be able to see these patterns. And it turns out that that is completely wrong. And it's wrong for an extremely interesting reason. So the question is, are these stochastic patterns, is their amplitude fixed by the level of the noise? And the surprising answer is no, it is not. Okay, and it's not because when you write down these PDEs, like the ones that we've got here for the Turing patterns and so on, these differential operators turn out to be non-normal operators. I'm just going to show you that, and that leads to a giant amplification of the amplitude, so the system undergoes an instability and then goes way beyond the linear regime. So let me explain how we do this. I'm going to be very quick, okay, because I want to get on to a little bit about neuroscience. So just take a dynamical system near a stable fixed point, okay, a stable fixed point. So all the eigenvalues are negative, okay? So what you're going to say is if I make a perturbation, how is it going to decay? You're going to say that the time decay is going to be some exponential time decay in time like that. That's what you've always been taught in your classes, and it's absolutely true as long as the operator here, the linear stability operator, is a normal operator, has orthogonal eigenvectors. But if the operator is not normal, that means it doesn't have orthogonal eigenvectors. And then what happens is that when you do the perturbation, what happens is its behavior is non-monotonic in time. First of all, it grows, and then it decays. And how it does that, I'm not going to go into the details here. Oh, here's the reference. We had a PRL in 2017, which explained all the mathematics of this. You can work out what the amplification is. I don't think I'm going to explain that for you. But the point is that this non-normality that leads to this non-monotonic behavior of perturbation, so they get this giant amplification into the nonlinear regime. This is a property of systems that are out of equilibrium. They don't have the symmetries that detailed balance would give you. And so the fact that you're in a non-equilibrium steady state means that this non-normality is pretty much guaranteed to occur. So there's that. What do I want? Oh, yes. Here's an example. So one of the students here in their projects showed an example of an equation which is kind of like a Brusselator equation. I don't remember who it was. And I made a comment when they were presenting their presentations this morning. Who was it who was writing a stochastic? Was it you? Yeah. Okay. So here is an example of this. So this isn't exactly the same equation that you were looking at, but it's something similar. So this is these sets of equations here for some reactions with diffusion, and then we worked out what happens for that. And so you can see here, this is the analog of everything I've shown you today for the stochastic Turing patterns. So this is the ratio of the diffusivities. So this is the regime here. This is the only regime where your deterministic PDEs will give you a Turing pattern. Okay? Here, in this blue, this is where you will see stochastically generated Turing patterns. So most of the pattern formation that occurs, if you're not doing individual level model demographic stochasticity, you will miss most of the pattern formation regime, and that's why I was suggesting that you perhaps consider that. So that's so you can see that in this paper that we wrote in 2017, and here I've drawn what have I drawn actually? A snapshot of the system, looking at showing you that you get actually large amplitude stochastic patterns. Okay, so now I want to talk about visual cortex. Can I talk for like 10 more minutes? Okay. Okay, so here's the reference, and here's the question. Okay, so what do you see? What do you see? Anybody see anything? What do you see? You see white? Somebody say? Yeah. Anybody see anything else? You see something else? What do you see?
Like green and pink, maybe?
Green and pink, okay, that's good. Okay, so what you should be looking at is your visual cortex. Okay, okay, so, okay, what do you see here? What do you see? Yep, a whirly swirly thing, right? Okay, did anybody see this last time? When I showed in the previous picture. Did anybody see this? Did you see this in green and pink? No, not you. Did you see this in green and pink, David? Did you see this here? Yes or no? Important question.
The colors, you mean?
When you said you saw colors, were you seeing this pattern in those colors?
No, no.
Okay, phew, okay, because this is your visual cortex on LSD. Okay, this is literally what you see if you take LSD or if you get hit on the head or something like this. Okay, so this is from a book by Kluver on hallucinations. So where does this pattern come from? Why? And that's easy to answer. In fact, why don't we see this pattern all the time? That is a hard question, actually. And then, what do we learn about vision from the fact that we are not seeing this all the time? So this is a hallucination pattern. Okay. And the question you should be asking is, if we can see a hallucination when you take LSD, well, why, well, you get hit on the head, why don't we see it all the time? And so what's happening here is this. This pattern arises from the spontaneous fluctuations of the neurons in the visual cortex. So you've got neurons in your visual cortex, and they will fluctuate, and when they fluctuate, they will produce this pattern. Now, how do we know that? Okay, I'm going to, since time is short, I'll try to be very quick, and I may say it again in a minute. Basically, what happens is this. When you write down a field theory that describes the way that the neurons are coupled in the visual cortex, that field theory, I can linearize that field theory and look at its stability matrix. That stability matrix has eigenfunctions, and those eigenfunctions can be classified. It's quite easy to do that in terms of their symmetries and things like this. And then what happens is those eigenfunctions are then put through a map. So what you see in your visual field and what your brains are seeing are related by a map called the retinoptical map, which is a complex logarithmic transform. So when you take the eigenfunctions of the stability operator that describes the fluctuations of the neurons in the visual cortex, they will then appear like that. So that's why you see that. Okay. So the underlying mechanism for this hallucination is a Turing instability, and it can be excited by intrinsic neuronal noise. Neurons are constantly firing and flapping around by just their own stochasticity, and when they do, they will excite these modes. Okay, so we would see those patterns all the time if our brain was just some randomly connected neural network. Okay, so suppose that you were seeing, suppose that was what was going on. Suppose your brain was a randomly connected neural network. The spontaneous fluctuations of the neurons will produce this pattern going through the retinoptical map, and this is what you see. Okay, that would be great, except that suppose what's in front of you is this. Okay, if that's in front of you, and you're seeing this, what's going to happen to you in the next second? You're going to be lunch. Okay? So the spontaneous fluctuations of the visual cortex to produce these hallucinations are really bad from the point of view of evolution. There is selection pressure. So if you are one of the people who look at the blank screen, and when you look at the blank screen, you see this, you're going to be eaten by this, and so you are going to not be enriched in the population. Very, very dramatically not be enriched. Okay, so the speculation is that evolutionary constraints have shaped the large-scale architecture of the primate visual cortex. Now, why is that? Well, I'm going to just show you the phase diagram. I'm not going to do a calculation. I'm going to ask the following question. If I've got a random neural network, I will see these hallucinations. What architecture of the brain will be the one that is least likely to have the visual field contaminated by these spontaneous visual hallucinations? And I'm going to show you that in a second. I want to mention that there is a mathematical similarity between the generic models of neural networks and predator-prey ecosystems. And the reason for that is this. You have two sorts of neurons in your brain: excitatory neurons that excite themselves and excite other neurons, and inhibitory ones that inhibit themselves and inhibit other neurons. So the excitatory ones are like the predators, and the prey are like the inhibitory ones. The range of the interactions, like here's a neuron over here, here's a neuron over here, that range is like the diffusion coefficients. So you can write down these mathematics, and they look very similar. This analogy was first was first mentioned by Jack Cowan, famous mathematical neuroscientist, in his PhD thesis. Okay, I'm going to skip all of this. I want to show you we do the calculation. Everything that we do is like what I just showed you on the blackboard. We're using a model which is called the Wilson-Cowan model. This is the retinal optical map. This is the thing that takes the visual field and then the visual cortex coordinates and transforms them. It's a conformal mapping like this. So this is the visual cortex, this is the visual field, and you put them through this logarithmic spiral. So if you take, this is what happens if you take the Turing pattern instability. Yeah, what? Yeah, I'm pointing on my laptop because I'm an idiot, yeah. This is what happens, thank you very much. This is what happens if you look at the Turing pattern instability, you stick it through that retinal optical map, and that's how you get the hallucination pattern. So let me show you what we did. So we took a generalized model of the visual cortex. We solved for the one loop fluctuations to work out the phase diagram, and then we asked what kind of architecture would allow you to not have the hallucinations. So are the hallucinations robust with different wiring? So here is the phase diagram. So these are coupling constants. They tell you about the connectivity of the different types of neurons. So basically, this here is the range of inhibitory connections. So let's have a look at this phase diagram. So first of all, these little sliver here and this little sliver here, that's where the deterministic mean field pattern formation occurs. Virtually nowhere. Now you look at the fluctuation-driven patterns, and they occur in, say, this region over here. This is another kind of instability which is related perhaps to neuronal avalanches. And the state that you want to be in is the state of working vision, which is a homogeneous state, and that's the state in gray or green or whatever this color is over here. And you can see that if you want to be in a parameter range where you have the largest region of working vision, you want to be over here. This is where you have the largest region. Over here, it's too small, and it's monotonically decreasing, so this is where you want to be. What this corresponds to is that you have very sparse long-range inhibitory connections. In other words, most of the connections are excitatory and they're short range, and there's occasionally ones that are long range and inhibitory, but most of them are not. So sparse long-range inhibition, which is in fact the architecture of the visual cortex, has the effect of controlling noise. Now there's another thing that's very interesting. Can I go on and then answer your question, please? Okay. So there's another thing that's interesting. When you look at what the patients report for their hallucinations are very regular. Okay, so you're probably saying, well, okay, if I've got stochastic generated hallucinations, they should be random. But when people draw their patterns, they're all very regular, like they're all very regular, like you can see over here. So why is that? Why are the reported hallucinations regular? And you can see that over here as well. So let me show you by going back. If you look at this part of the phase diagram, so let's suppose that you've been hit on the head or you've taken LSD or something like this. You've gone from this operating state up this axis here, and the thing that you run into straight away is the mean field phase diagram, where you have deterministic, periodic Turing patterns rather than random ones. You've got a chance to be up here. There's a little sliver of the fluctuation-driven patterns here, but most likely you'll go up here, and now you'll be in the mean field pattern formation regime. So what happens is that this explanation then also explains why the hallucinations that you see are regular rather than patchy. Okay, so that's the end. That's what I wanted to tell you about with stochasticity. So I'm on time. I do have so that's the end of my lecture. Before I finish, before you ask me questions and things, I did produce a a hands-on project for you to work on, and that will be explained to you by Ricardo and Veronica next week, and it's interesting and fun, and I hope some of you do it. So I'll answer your questions first, and then if there's any time, I can just tell you a little bit about what that project is. But let's that's the end of my talk. Here's my summary. Demographic stochasticity can give population oscillations and spatial patterns where they cannot exist deterministically. You don't need fine-tuning. There's less parameters. You get a correct treatment of fronts, spatial boundaries, critical transitions. I didn't talk about rapid evolution. That's the hands-on project. Stochastic Turing patterns can be observed in the laboratory, and suppression of generically expected stochastic patterns by the architecture of sparse long-range inhibition yields a prediction for what would be the functional state of the visual cortex, subject to evolutionary pressure and the developmental plasticity of the visual cortex. So, okay, that's it. I'm done. Yep.
Hi. Thanks. I have a question about the power spectrum. There seems to be, even yesterday and today, the symmetry of omega and k. It seems to be like both decay and long range the same way. And how do you maybe immediately see this from the model, or in what way?
Well, I think it just, in these particular calculations, it just reflects the fact, well, the omega and k are decoupled, and this mechanism more or less is the same in terms of space and time. So that's just what happens. I don't have any deep. I mean, I don't know if there's a situation that I've run into where omega in the tails would go as, say, omega to the -6, and in space would go as k to the -2. I don't think I've seen that. But I also can't tell you that it doesn't happen. So, okay.
Hi there.
Yeah.
In phase separation, you have nucleation and growth, which is a phenomenon induced by noise as well, right? And essentially, you increase the pattern formation region typically by just a little, right? In your case, the enlargement of the pattern formation region through noise is quite large. Is there
huge?
Is there a reason for that?
Yes, because here we're looking. There you're looking at the kinetics of a phase transition, and all the noise is doing is really making the thing get started and so on. Here we're looking at systems in a non-equilibrium steady state. So they're different. I think Owen has a comment on that too.
Comment or question, because I don't know. More of a question. So are your systems sub or supercritical? Because if they were to be subcritical,
they can be subcritical too. Yes.
Yeah, and that has an effect, I guess, on the role of noise, right?
That's right. If it's subcritical, then that's this is like what I was saying when I was talking about the difference between nucleation and spinodal. That if you're in the nucleation regime, it's like a first order transition. You have to get over a barrier. Okay, so the noise is there to kick you over. If you're looking at a phase transition to kinetics and it's supercritical, which means you're in the spinodal decomposition regime where there's no nucleation barrier, it's just a long wavelength instability, then the noise has a different effect, and in fact it actually basically has no effect whatsoever until the final stages of the growth, as we discussed. But in these stochastic Turing pattern things, the big difference is these are non-equilibrium steady states. Okay? And they're driven out of equilibrium by the particle birth-death processes, the predation and the birth and death and so on. So they're not in thermal equilibrium. Okay, did I answer your question? Yes. Wait, I can't hear. Can you give him the microphone, please?
So just that in motility-induced phase separation in active matter, you also have only a small enlargement of the pattern formation region through noise, and it's non-equilibrium as well.
It's non-equilibrium.
But it's conserved dynamics is different.
That's true, but again, you're looking at a transition. You're looking at it like a non-equilibrium version of, say, spinodal decomposition, but you're not looking at a non-equilibrium steady state. Okay, these are steady states. Okay, they're not Gibbs states; they're non-equilibrium steady states. So that's the difference. So even in motility-induced phase separation, it's still pretty much the same as spinodal decomposition in thermal equilibrium, except you can have non-potential terms in the equations of motion. Do you have a comment on that, Owen?
I'm coming.
So I just can share about my intuition about MIPS, so or spinodal decomposition, so Kahn-Hillard dynamics. You have this critical behavior where you have spinodal decomposition, and that's surrounded by behavior where you have a finite barrier. Mm-hmm. So it's shielded in a way, the regime where you have pattern formation by spontaneous fluctuation is shielded very strongly by first order effects. Mm-hmm. And that's why fluctuations don't play such a role. Yeah. That's my intuition.
Well, it's one reason.
That's one reason. Yeah,
I mean, the other is the length scales.
Yeah.
Yeah. Yeah, just to make clear about my comment about length scales. If you have a system near thermal equilibrium, and you ask, where do I see the effects of thermal fluctuations? The answer will be in the width of an interface. So I have a correlation length in the system, which tells me about the fluctuations, and the correlation length sets the scale for the interface, for the width of the interface between domains. So I'm using those two things the same. So when I say the pattern size is growing to infinity and the width of the domains is not, that width of domains includes the effect of thermal fluctuations that give you the correlation length. And so so that's why these things we're saying the same thing in different language. Okay, so does that answer your question? Let's go on to the next one. Yeah.
Thanks for the talk. I was wondering about like your computation of the power spectrum, because if I see this correctly, like you're basically calculating like the one loop correlator.
Yes.
And you probably want to avoid like calculating all these like Feynman graphs.
I want to do what?
You want to avoid calculating the Feynman diagrams explicitly, right?
Oh no, you can do that as well.
Okay, so you could also.
We've done that. Yes, I'm just showing you a sequence of very dirty tricks to get the answer in less than 2 weeks of lectures.
Is this?
You can do it. You can do it perfectly well by Feynman diagrams and get the same answer.
Or this like expansion to like higher orders of the stationary phase.
Yeah.
Okay.
We did that, and Uwe Teuber has written quite a lot of really nice, very detailed review articles about how to do that and get the same answer. And in my notes I give some references, and particular Uwe's lovely book on critical dynamics, which has all the calculations in gory detail and so on. So I'm just, for pedagogical reasons, I'm using my experience to try to find quick ways to convey the same results. So what we did here was Martin Sidger-Rose and Feynman diagrams and everything, but you never had to be exposed to the horrors of all of that.
Thank you.
Okay? Yeah.
So I'm wondering about how universal it is that that noise will expand the range of pattern formation, particularly in light of yesterday when I showed these bush balloon pictures.
Yeah.
I can imagine if you have an internal equilibrium which is positive, you're on the side where patterns more easily develop, but you will extend the range. But if you would go to the other side, where actually the homogeneous equilibrium doesn't even exist, you only have the pattern state being able to survive. Is it possible that at that stage the noise would reduce the range of pattern formation?
Okay, so but I don't know if that microphone is on. So your question, actually, I'm trying to paraphrase your question. Did I understand it?
So if you take a range...
So hang on, let me try to pose your question. So are you asking, the Busse balloon is what we call it, say, in fluid convection, which is a regime where you're above the neutral stability curve, so the uniform state is unstable to forming a pattern, and the pattern has a range of wavelengths that it can have between the edges of the Busse balloon, and at the edges of the Busse balloon tell you where the instabilities, like the Eckhouse instability and so on, kick in. And so you're asking, do fluctuations increase the size of the Busse balloon? Is that what you're asking?
On one side, it most likely will. I mean, that's what you showed, that at least I think your examples had an internal equilibrium, homogeneous equilibrium, if I use the right terms. But on the side where actually the food supply is very low, could it also limit? Could noise limit the persistence of the existence of?
I don't think so, because I think the noise that you were talking about was not demographic stochasticity.
I don't have noise. I'm just talking about your.
Oh yeah. So if you just have thermal fluctuations, they hardly make any effect on the Busse balloon, except very near the onset of convection or near the onset of the instability. So they are not very important for the pattern formation in those systems. Yeah, I don't think these. It's an interesting question. I don't know if there's a Busse balloon analog. Well, okay. So you would say, in your Busse balloon language, I know it's nice to say Busse balloon all the time. Where did I have the phase diagram? Somewhere here. Okay, here. So what you want to say is, you want to say this is the Busse balloon. Well, actually, the Busse balloon would be here. So the analog of the Busse balloon would be this region where Turing patterns are stable. And then you could say, did the fluctuations enlarge the Busse balloon? Well, I suppose you could say, yes, they did. So this is the stochastic. But remember that the patterns in here and the patterns in here are not the same. The patterns in here are perfectly regular, and the patterns in here are stochastic. So they look different, and they have different correlation functions. But basically, you're right. You're right that it's a huge effect here. But that's
yeah. In the interest of saving the coffee break, I think.
Okay, right.
If you want to say a couple of words about the project next
week.
Okay,
sure.
If you want.
Sure, very, very quickly. Okay, you will hear more about this next week. I want to tell you about the project. Okay, here. Okay, so what is the project? So you've heard about pattern formation in predator-prey dynamics. So the project is to do pattern formation in predator-prey dynamics, but with evolution. Okay. Okay, now evolution makes a huge difference. And the idea is this. What happens when you have predator-prey with evolution in space? Okay, all of it, everything all at once. So the answer is we don't know, because we were going to do the calculation, but we never did, because we started working on turbulence instead of that. So the experiment has been done without spatial resolution, and we've done the calculation without space. And here's what you get. I'll show you this. What you get in space, well, I'll just tell you. What you get without space is that you know how the predator-prey cycles are 90 degrees out of phase? When you have evolution, they become 180 degrees out of phase. Okay, and I'll show you the data in a second. And we did the stochastic theory, and it predicts exactly what you see in the experiment. Now, what we didn't do is what happens in space. Okay, because we had something more interesting to do, so we went off and did that. So here's the idea of the project. Okay, we're going to have two teams. Okay, two teams. So one team are the computer simulators, and team two are the people who understood more than, say, 30% of today's lecture. Okay, so those people, so team one will adapt a net-logo simulation of an individual level model of predator-prey, either the energy model or particle model, and what you're going to do is you're going to include in that the evolution of a mutant, and the mutant is one that is able to resist the predator. And I'll show you why we know that that's the mechanism. So the mutant has a lower metabolism. In other words, it has a lower fitness compared to the wild type. But when you have predation, the mutant is actually more enriched in the population and can even go to fixation. And so that's the origin of these weird cycles. Okay? So one team will do that, and then team 2 will do the theory calculation, which we already did, all the path integrals and everything, and all of the annihilation creation operators and everything like that. We did it without space, and now you can add space. Do you see patterns? Do you see traveling waves? What happens there? And then, if let's suppose everybody in the room decides they're going to join one team or the other, then if it all works and the simulations and the theory agree, then we can all write a paper together. A paper in theoretical ecology with 50 authors. And that would be just amazing, because people would think it's high energy physics because it's got 50 authors and it's got Feynman diagrams and field theory and everything like that. Okay, so I'm going to just show you. I'm not going to go. I know you want to go to tea. I'm going to just show you some slides I put together from my student Hongyan Shi, and I just want to show you the data, just so you know that this is a real thing. Okay, so here is data on the bacteria ciliate system, and you can see that the phase difference between predator and prey is pi in these cycles, not pi by 2. And then here's another system. This is Bochanan and Lenski. They had a bacteria and they had a phage, and they were measuring predator-prey cycles in the bacteria and phage. So here's what happened. So they started doing it, and you can see the red and green, the cycles. The red is the predator, the green is the bacteria, red is the phage. And you see cycles with about pi by 2, and then all of a sudden the mutants. A mutant, which is a bacteria that has got some defense to the phage, and then suddenly, wow, the bacteria now has hardly any visible oscillations, but the predator now, its period has doubled. And those are called cryptic cycles. And then, so you can actually then go and do the theory, and we worked out the theory, we simulated it just to check. Sorry about that. So we did the theory to check, and you can see here, this is what happens in the simulation, and this is what happened for the cryptic cycles. So we understand this thing perfectly for a well-mixed system, but we never did it for space, and I think it would be cool to do it. We were going to do it, but we just never got round to it. So there you go. That's the project.
Cool. There will also be projects that do not involve either. That do not involve quantum field theories, hopefully. But so thanks a lot, Nigel, for this beautiful series of lectures. Very inspiring.